So we've just finished quiz number 3. No more quizzes this semester. That's the good news. If we look at some announcements here, remember homework 12 was pushed back by a couple of days compared to what the schedule said. The schedule that I gave you at the beginning of the semester indicated that that would be due today, but instead it's due before class on Friday. The design project final report is due Monday of next week, and then Friday of next week is the last homework assignment, and our final exam will be on Tuesday the 23rd. And we've got 2 hours for that exam here in class, and so that's going to allow me to give you more questions than I have on previous tests where we only had 50 minutes. So, you know, sometimes there's a risk that if there's only 3 questions on an exam and it doesn't have to be something that you've studied well, then it's kind of like a disproportionate penalty or not really representative of what you learned. And so my hope is to have a little bit smaller questions, but more of them for the final, so that there's like a wide range of topics that are covered, and it's a pretty good assessment of what you learned. The exam's comprehensive, and so it's going to include questions from the first part of the course, back when we were doing closed conduit flow. It'll include some of the more recent material as well. In fact, there's going to be added point emphasis on the things that you haven't yet been tested on. So the information since exam 2 is going to have a disproportionately high number of points. Although it will be comprehensive, it's going to be weighted more towards the recent material. There will not be a water gems question on the final exam, and so you don't have to bring a laptop with that, but you should bring a laptop with access to Excel, because we've been using Excel all through the semester, and you know, a good number of analyses you need to be able to do require Microsoft Excel. So does anybody have any questions related to the announcements? By the way, did everybody watch the eclipse on Monday? Yeah. I already told you that I went up to Ohio to watch it. It was awesome. I mean, totally worth the drive. You definitely, if you get the chance to go like into the zone of totality, you should go for it, because I mean, it's cool to see it like almost eclipsed, but all the way eclipsed is like 90% better. So give it a shot sometime. We're going to do another example related to the direct step method today, just to reinforce that technique. I wanted to reiterate some of the assumptions that can apply when you have a wide channel. And so if you have a wide channel, meaning that it's more than 20 times wider than it is deep, then Manning's equation gets a little bit simpler. You know, finding the normal depth doesn't depend on the effect of the edges, and finding the slope of the energy grade line is also easier if you have a channel which is considered wide. And specific energy is basically the same. It's still depth plus velocity head, but remember the simplifications that apply only when the channel is wide. And don't be tempted to use these formulas if the channel isn't wide, because it won't give you the accurate slope of the energy grade line or normal depth. Okay, so let's review the direct step method. This was the subject of the recorded class meeting from Monday's class, which was posted on YouTube. And the idea here was we wanted to know a length of a backwater curve. The example that we worked, we had an M1 profile, meaning that it was a mild slope, some sort of an obstruction that was causing pooling upstream of the obstruction. And in the example, what we wanted to know is how far upstream of that obstruction do you have to go until it's flowing back in its steady, uniform condition and achieving the normal depth. So what we did was we calculated what was the depth upstream of the obstruction, which was basically just the critical depth over the obstruction plus the height of the obstruction. That's how we found that first Y, what here is described as Y7. And then rather than just trying to go all the way from upstream of the obstruction to the normal depth, we broke it up into segments. And does somebody remember, like conceptually, like what's the basic idea of why we break it up into multiple steps instead of doing just one step the whole way? Anybody want to speculate? What's the shape of the water surface look like? Is it a line or a curve? I think Elaine knows. Curve, you're right. It's a curve, yeah. And when we applied the direct step method, what we're doing is we're saying between 2 points, there's a distance, and we are treating it as though it's a line. And so I think I illustrated this early on when we were talking about gradually varying flow, that if we have some obstruction and here's the water surface, what we have to do is treat it like a bunch of line segments, because multiple segments, it's not so bad to treat that as a line, even though it's slightly curved. And it's okay from here to treat that as a line, because it's not too deviated to say between there the curve can be approximated as a line. But if we tried to go all the way from y7 to y1, if we extrapolated the slope of the curve at that point, it's not going to intersect the water surface. And so that's why we're breaking it up into pieces. Is it's the conundrum is representing a curved water shape with a line. So the more segments we break it up into, the more accurate it is. Or the other way to think about it is, like in Monday's class, I suggested that at the upper limit, you should never have a water surface change greater than ½ meter. And that's kind of an arbitrary threshold. The reality is, the more pieces you break it up into, the more accurate your estimate's going to be. So for example, if we had only 2 segments, like that's more accurate representing a curve by a line if there's 2 segments than if there's just 1. But the more pieces we put in, and the smaller the change of elevation between the segments, the more accurate it will be. And there's kind of a point of diminishing returns, and we'll take a look at that with our example today. So the process is find the energy difference between locations, average slope of the energy grade line, and then calculate the segment length. Okay, here's the example we're going to work through today. Let me give you this handout, and because I want to leave enough time for us to go through the spreadsheet part of it, what I'm going to do is just show you the calculations for A and B. And you can copy it down, and if you don't get it all, you can come back to the video later. But we want to start off by knowing what's the critical depth and the normal depth. Okay, so water's flowing under a gate. You can see from the diagram here, it's saying this is an S3 profile. If it's an S3 profile, what does that tell us about the slope? Steep. It's a steep slope. Good. And steep is not like a qualitative description. That has a technical meaning. It means the slope is greater than the critical slope. So it supports supercritical flow on this slope. So water comes out from a gate and it's supercritical because the gate kind of pinched down the depth, and it's going to stay supercritical. But the question is, you can see here from the question marks, how long from when the depth was 0.9 meters is it going to take? What's the distance for it to get back up to its normal depth? So we have to know what is the normal depth, and then we want to verify that this is an S3 water surface profile. And so to do that, we can compare the normal depth to the critical depth and so on. So let's take a look at these calculations here. So first thing we do, find the normal depth. Manning's equation is what we use for normal depth. This is a rectangular channel, but it's not a wide channel. So we can't use that abbreviated normal depth formula that I showed you just a few minutes ago. We have to say, The flow rate's 36 cubic meters per second. The area, you can see the bottom width of the rectangle is 2.75 meters, and so area is bottom width times depth, since it's rectangular. So area to the 5/3, slope to the 1/2. The slope of this channel is 0.7%. So 0.007. So slope to the 1/2, and then in the denominator, the n value, 0.015, and wetted perimeter to the 2/3 power. Wetted perimeter is the bottom width of 2.75 plus 2 times the depth to take into account the sides. So if you put that normal depth formula in with all the parameters we do know, that it's going to go back up to 2.534 meters. So if we just briefly take another look at the sketch, it starts at 0.9 meters and it's going to gradually increase until it gets up to 2.5, what was it? 2.534 meters. All right, so part B said find the critical depth. That's even easier. You know, since it's rectangular, we can find the flow per unit width, lowercase q. So that's 36 cubic meters per second divided by the bottom width of 2.75. That gives you 13.091 meters squared per second. Pop that into this equation for the critical depth. The critical depth is 2.592 meters. So this is interesting. This is just barely supercritical flow. The fact that the normal depth is only slightly less than the critical depth tells us this is just barely supercritical. If we had calculated the Froude number, it would be above 1, but not by a lot. But anyways, we know the flow depth at a certain location of interest is 0.9. We know the critical depth is 2.59, and the normal depth is 2.53. So those three things, the flow depth, critical, and normal, is what allows us to classify the water surface profile. So you can see here this statement that the flow depth is less than the normal depth, which is less than the critical depth. That confirms it's an S3 profile. So S means that you've got a steep slope. So anytime the normal depth is less than the critical depth, that tells you you've got supercritical flow, and therefore the slope is steep. So we get S by this. That tells us it's an S slope if the normal depth is less than critical. And then the 3 part of it comes from being in zone 3. The given flow depth of 0.9 is beneath both normal and critical, and that's zone 3. So S3 profile confirmed. So any questions so far on the setup of this problem, direct step method? Now the question is, how long does it take for it to gradually increase in depth from 0.9 up to the normal depth? And I intentionally made it so this would be a pretty long curve. And what's going to make it long is that this slope of 0.7% is very close to the critical slope. So when the two are pretty close, then it takes a long time to find equilibrium again. So let's go through. I put another template file on Blackboard. If you want to follow along with your laptop, that new example 2 template file is there. Let me show you. It's slightly different from the template file that's included in the lecture video from Monday, because what I did was I wrote Manning's equation in terms of wetted perimeter instead of having hydraulic radius as a parameter. So you'll just notice here the slope of the energy grade line, that formula is slightly different from the template file that we worked through with Monday's example. And then because of that, I've added a column with wetted perimeter, because we're going to need to refer to that when we calculate the slope of the energy grade line. Okay, so we want to find out how far is it, distance, from depth of 0.9 all the way up to depth of what was our normal depth again? 2.534. So with the template file, what we'll do is put in the segments that we want to calculate for. So starting at the depth of 0.9, And just as a first try, let's go from 0.9 to 1, and then a depth of 1.25, then a depth of 1.5, 1.75, 2, 2.25, 2.5, and then finally, oh, I need to add one more row, I think. So 2.534 is the normal depth. And I'm going to delete this and add the borders. So what we're going to do is find out what is the length of the segment where the water goes from 0.9 to 1 meter in depth. What's the length of the segment where it goes from 1 to 1.25 and so on. Okay, let's put in some of the parameters we know. The width of the channel is 2.75 meters. The flow rate is 36 cubic meters per second. The slope of the channel bed is 0.007. And the end value is 0.015 for this. Okay, so it's rectangular channel. Cross-sectional area is depth times width. So equals depth times the bottom width. And I'm going to anchor the reference to the bottom width there by pressing F4. So it always looks up there where it's 2.75. Okay, wetted perimeter is the bottom width, anchor the reference there, plus 2 times the depth. 2 times whatever depth for the row that we're on. And that gives us the wetted perimeter. Velocity is the flow rate, Q. Anchor that reference since we're going to be dragging this cell down multiple times. Velocity divided by the area, which we just calculated moments ago. So we got the velocity. Specific energy, remember, is depth plus velocity head. And since I've just calculated the velocity, then that's easy enough to find the velocity head. So specific energy equals the depth plus velocity head, which is V squared divided by 2 divided by G, 9.81. Okay, so we've got the specific energy, velocity, perimeter, and area. But we've only got it for a depth of 0.9. So highlight all of that, and we're going to just copy and paste those formulas down through all of the other depths. So I'm keying in Control-C to copy and Control-V to paste. Paste. For each of these depths, I want to paste it and calculate the appropriate parameters for whatever depth in question. Okay? Now the reason why we've put in this extra row is I want to know the delta E between the segment. So between the top end and the bottom end of the segment, how much energy change is there? And so here, the delta E I'm going to do equals the deeper water specific energy minus the shallower water specific energy. So as the water flows from a depth of 0.9 to a depth of 1, you're losing 1.949 meters of specific energy in that segment. Okay, so then I can do the same thing, just kind of like pasting that for each of the different segments. Find out how much specific energy is lost in the segment in question. Okay. Now, S sub F. We're using this formula for S sub F. So it's rearranging Manning's equation to find the slope of the energy grade line. So equals, parentheses, the n value, anchor the reference, times the flow rate, anchor that reference, times the wetted perimeter to the power of 2/3. So I'm going to say to the power of 0.6667. and then divide that by the area to the power of, parentheses, 5 divided by 3. Or you could do, I guess, 1.6667 if you don't want to put in the parentheses and all that. But I've done all of that. Now I need to close parentheses and then square the term. Because you'll notice here on the outside of the term we square everything. So the slope of the energy grade line for this segment, and so I need to paste it again for each of the rows that I'm on, because the slope of the energy grade line is going to be changing as the shape of the water surface is changing. All right, so now the average S sub F is saying between where the depth is 0.9 and where the depth is 0.1, what's the average slope of the energy grade line? So it's just the average of the upstream segment plus the downstream segment. So upstream plus downstream divided by 2. So it's the average of this one and that's the average that applies in between them. And again, well, let me not do the copy and paste thing because I'll do it later when I have these other two rows. Okay, slope of the energy grade line minus the average. So I'm anchoring the reference up here to the slope of the energy grade line minusing the average that I just calculated. And then the DL, the formula for that is this one. Okay, so DL is the delta E that we'd calculated way over here divided by the slope, channel bed slope minus the average energy grade line slope. So for example, this is saying that the water, when it goes from 0.9 meters to 1 meter, the length of distance that it takes to do that is 22.51 meters. And so let me now copy and paste this for each of the segments, and then I have to add them all together. All right, so then the total is going to be the sum of all these little pieces. It tells me how long the distance is for each piece. The total downstream distance is 367 meters. Most of these segments we were doing in quarter meter depths. Just to show you one thing, because I've got 1 minute left. If we had instead done it as smaller steps, like if I broke it up instead of quarter meter, what if I did it in tenth of a meter steps? So 0.9 to 1 to 1.1, 1.2, and so on. So when we did this kind of coarse mesh, bigger steps, it was 367. My guess is improved the smaller the steps I do. And so it says 380 if I do it in these tenth meter steps, or if I do it in 0.05 meter increments, it says 384. And if I got even smaller, it would be pretty close to 384. But I just wanted to point out that the more rows you have, the more accurate the estimate's going to be. But the direct step method, nonetheless, is just meant for us to calculate how long it is for the water to gradually vary towards its normal depth. All right, it's 11:50. That's all the time we have for today. I'll see you on Friday. Just remember that homework 12 is due before class on Friday.